Welcome back, AP Statistics students. We are looking at Lesson 5.2b, which focuses on the addition rule for probability. In 5.2a, that lesson, we looked at some of the notation and some of the language that really deals with probability. And we're going to dive deeper in that today and hopefully further our understanding of it. To help us, we are going to use the mathematical lesson, which focuses on the question, is there a connection between those who can taco tongue and those who can evil eyebrow? So some people believe that there is an ability to taco tongue and evil eyebrow is something that you are born with. Now we're going to look at the classroom data and see how these two abilities are related. So can you taco tongue is can you create a taco with your tongue? And can you evil eyebrow, which of course Ms. Rainsberg can evil eyebrow. So can you taco tongue or evil eyebrow? And we're going to collect that data. So let's go ahead and get started. As I looked at some data already, and I have a classroom set of data, 30 students. You can see that in the total down here in the table. There are 30 students, and 15 of them could both taco tongue and evil eyebrow. Now, 5 of them could taco tongue, but not evil eyebrow. 3 students could do the evil eyebrow, but could not taco tongue. And then there were 7 students total who could not do either. They could not taco tongue, they could not evil eyebrow. So you can see a total breakdown of everything going on. We have 18 students in this class who could do the evil eyebrow. Of those 18 students, 15 of those could do both taco tongue and evil eyebrow. So this is a way of us looking at a two-way table. And this is something we discussed way back in chapter 1, is a two-way table can organize information, and we have to understand that the intersections of the rows and the columns have meaning to them. So if I look at this intersection right here, that is no evil eyebrow, but yes, taco tongue. So that is someone who could do the taco tongue, but can't do the evil eyebrow. So we have all of this data, and what we're going to do is we are going to transfer it over to a Venn diagram. And so that is what this is over here. This is a Venn diagram. And when you transfer it, it's really, really, really important to understand where is the starting point. And the starting point that we're going to focus on is we're going to focus first on who can do both, because they're talented. And if we focus on who can do both, that is going to be this section right here. Because that section is where the taco tongue intersects the evil eyebrow. And so those represent the people who can do both. And so if I look at it, I see that there are 15 total people right here, 15 total people who can do both. They can both taco tongue and evil eyebrow. So now we want to focus on what's going to happen next, and that is, okay, hey, how many total people can taco tongue? And there's a total of 20 people who can taco tongue. Well, I've already got 15 in that circle, in that Venn diagram. There's already 15 there. So really, guess what that means is I need to put 5 more here, because that would be a total of 20 in that circle. 15 in the intersection, and 5 who can just taco tongue, but they can't evil eyebrow. They're not actually in that evil eyebrow circle. And so we can see how that represents the 5. And so now let's figure out the other one. So if we look at those who can evil eyebrow, and so if I look at the evil eyebrow, this circle right here, the number of students who can evil eyebrow is 18. 15 of them were already accounted for because they're very talented and can do both, which means that 3 of them have to be here. So we can see there's 18 total people who can evil eyebrow, but there's only 3 who can evil eyebrow, but they can't taco tongue. And so we can see how that 3 relates inside of this table right here. Those are 3 people who can evil eyebrow but not taco tongue. So you may go, okay, well, that's everyone accounted for, but it's not. There are some people who have been left out. There are 7 people in that class who could not do either. And so those are the ones who are completely outside of both circles. And so this is a way of kind of introducing the two-way table and the Venn diagram to us so we can understand what's going on. Now we can use this to help us find probabilities based off of the two characteristics. So I took our image here and I color coded it so we could understand everything a little bit better where they are. So we could see that the intersection of the 15 is green, and the yellow is the no evil eyebrow because they're not in that circle, but they are people who can taco tongue. So you can see how the yellow for the 5 right there is the 5 inside of that section. And we can see where the 3 is and the 7 is. So you can see some of the color coding, and I do have the 30 in the table. It's got highlighted in purple. That way we can focus on the total. There was 30 total students in there. And remember the rows right here, that 20 that we're looking at, that 20 is the total number of people who can taco tongue. And the 18 in the bottom column there is going to be the total number of people who can evil eyebrow. So let's kind of dive into just using the two-way table, or if you want to focus on the Venn diagram, to answer some of these probability questions. So the first one says, suppose that we randomly choose a student from class. Find the probabilities as fractions. Okay, so I'm going to leave them as fractions, not going to go into decimals. So probability of yes, taco tongue. So that is all the students who said they could taco tongue. Well, in that case, it looks like what I'm focusing on is I want every single student in this row. And so I'm thinking that's 20 out of the 30 students. 20 students said they could. So let's kind of just go down just so we can focus on what the next one is. Okay, what's the probability of no taco tongue? Well, that's interesting. That's kind of like the complement of yes, taco tongue. And so really, I'm thinking I'm going to do 1 minus, and that would give me 10. But I can also see it's right here in this row. There were 10 total students who could not taco tongue. So let's kind of do the same idea with the evil eyebrow. The evil eyebrow, and I'll use the Venn diagram for this one, is the evil eyebrow. There was a total of, well, if I circle it right now, I see there's 15 and 3. So there should be a total of 18. And I can see that in the two-way table right there, that there was a total of 18. No evil eyebrow, well, that's the complement of evil eyebrow. Those are the ones who go through. And so no evil eyebrow, I'm thinking there was 12 total who could not do the evil eyebrow. And I can also look at it this way and see there was 12 total. So the probability is 12 out of 30. So we have that idea, and notice how I kind of threw in the vocab complement because we're going to be looking at that again. So I want the probability of yes, taco tongue and yes, evil eyebrow. So in that case, that would be yes, taco tongue and yes, evil eyebrow. Well, they intersect right there. I'm thinking that's the 15 out of 30. So you can see the color coding there to kind of help you see where I grabbed that out of the two-way table. How about yes, taco tongue and no evil eyebrow? So again, I want yes, taco tongue, this row right here, no evil eyebrow. Well, they intersect right there at the 5. So I'm thinking that's 5 out of 30. And we can keep doing this, yes, evil eyebrow and no taco tongue. So yes, evil eyebrow, right there, no taco tongue, and they intersect at the 3 out of the 30. And I can look at no taco tongue and no evil eyebrow. Well, that person is completely left out of all the circles. That's 7 because I got no and I've got no. So they intersect at the 7 out of 30. So we have just kind of how to look at the two-way table, and we kind of even looked at the Venn diagram to help us out. And you've heard me use words like complement because we're going to start labeling the two-way table and the Venn diagram there with the probability notations to help us out. So let's move on to the next part of this two-way table and Venn diagram of taco tongue and evil eyebrow. So we have the same data here, and we can see what's going on. We can see now we're being asked something a little bit different. Suppose that we randomly choose a student from class. I want to find the probabilities as fractions still. Yes, evil eyebrow. Well, we've already done that one. I mean, that's just the 18 out of 30. No evil eyebrow. That's the complement of evil eyebrow, so that should be 12 out of 30. So those we have already answered. Now here's something interesting. Yes, evil eyebrow or no evil eyebrow. So what does that mean I want? I want yes, evil eyebrow. That's look like 18 out of the 30. No evil eyebrow, 12 out of the 30. Well, I'm just going to add those together. 30 out of the 30. 18 plus 12. So I have 18 over 30 plus 12 over 30. And that's going to give me 30 out of 30, which is 1. Now in this case, focus on my highlighting here. There's a reason why this problem's on here, and it's because of number 3. But if I focus on my highlighting here, yes, evil eyebrow and no evil eyebrow, they had no outcomes in common. And so because of that, I could add them directly together without any issues. And we call that mutually exclusive. If something is mutually exclusive, that means they have no outcomes in common. So that's actually a vocabulary word that we need to be aware of, is mutually exclusive means they have no outcomes in common. And when two events are mutually exclusive, when you have an or probability, and take a look at the notation, remember, probability of A or B is probability of A union, we'll get to that later. The U, remember, kind of like a boat, oars on a boat, point outside, that would float. And so A or B is probability of A plus the probability of B. Straightforward if they're mutually exclusive. And so that's really what number 2 is focusing on. So I wonder what number 3 is focusing on. If this is looking at mutually exclusive events, which are simple addition probabilities, you don't have to worry about anything because they had no outcomes in common, then I wonder what's going to happen in number 3. Same idea. Randomly choose a student, write the probabilities as fractions. We've already answered these probability of yes taco tongue and yes evil eyebrow back in question 1. So I'm just going to delete those and show you that the probability of yes taco tongue is going to be 20 out of 30. The probability of yes evil eyebrow is going to be 18 out of 30. Wait a second. Let's do that again. 20 out of 30, 18 out of 30. I'm thinking I overlapped right there at that 15. I counted that 15 twice. So we need to keep that in mind. So I want the probability of yes taco tongue or yes evil eyebrow. The issue is we counted that 15 twice. I took my 20 out of 30. I took my 18 out of 30. I counted that 15 out of 30 twice, so I have to subtract it. That way I can get rid of the one that I counted more than once. And so in that case, I would have my answer of 23 out of 30. That is the probability of somebody with yes taco tongue or yes evil eyebrow. So in this case, there was something interesting that happened. We had an overlap. The overlap is where they intersect. And so overlap is kind of the word I used before. We are now going to start calling that where they intersect, and that's going to have the word and attached to it. So the probability of A or B, same idea as the previous slide. But the issue is now they overlap. And so if I want the probability of A or B, what happens is I can take my probability of A, add my probability of B. However, what happened in this case was that they overlapped. I overlapped here and here, and I have to subtract it to make sure that I can remove the fact that I'm counting it twice. And that right there is the symbol for and. Probability of A and B, the upside down U that is read as intersect. And so I have to focus on that. This right here is the general addition rule. You need to be aware is this is what's going to happen most often is that if you have two events that have outcomes in common, and in this case they did have an outcome in common of that 15 students could taco tongue and 15 students could do the evil eyebrow. So that was where they intersected. I counted it twice. That's going to happen very often. So we call this formula the general addition rule formula because it is the one that you have to probably focus on the most. And in this case, it's because the events are not mutually exclusive. They do have outcomes in common. And so we're going to use the general addition rule. And good news is, well, what happens if they don't have any overlap? Then you just don't focus on it. It's 0 and you move on. So hopefully this helped with some of the notation and some of the understanding of the formulas. And let's move on to the next problem. And so the next part is just focusing on what we have learned so far, which is a lot of actual notation and really important things. So if you understood the taco tongue and the evil eyebrow example, now we're going to look at these symbols to help us understand what we're really dealing with. On the bottom, and we'll focus on the bottom part here, it's the probability notation because that we introduced right away at the end of the taco tongue problems in questions 1 through 3. So really what we learned, and we'll focus on the and. This symbol right here means intersection. We use it, you can see I have written down there for ands. It's event A and event B both happening. That was the 15 out of 30 for the taco tongue. So we read that as the intersection. It is the intersect, A intersect B. That is and. So intersection, and. Remember, it kind of looks like a lowercase n. And so if you think about the fact that you have and, that it looks like a lowercase n. And it can help you realize that you have an and. The next one we looked at was an or situation. And for an or, you would have called it a U. And really what that stands for is for union. And so you can see why we have that. It looks like union. It looks like the U for us. So that is read as union. We can look at it as or, A or B. And remember, we need to be careful if it's A or B, because if they're not mutually exclusive, they could have an overlap. Now that picture right here next to my head is a mutually exclusive. They have nothing in common. But if I look up here, we would be able to have ones where they do over here, they have an overlap, so these are not mutually exclusive. And so those are our rules that we're looking at, and we're trying to now organize it all with information. So let me give myself some space here and remove this and remove this. And let's focus on kind of labeling our two-way table just with our notation. And so if I look at it first, I'm going to put A right here. I have the probability of event A and I have the probability of event B. So we have that set. Now, what is the other column going to be next to A labeled? Well, if this column represents probability of A happening, then this column represents its complement, the probability of A not happening. Remember this column, yes, taco tongue, no taco tongue. That means that it was the complement, which probably means that this row down here is the complement of B. And so we can see what's going on with the notation in the two-way table. One row is the row of the event happening, the other row is the complement of that event, and same with the columns. And so what I have right here is I'm going to put the number 1 here, I'm going to put the number 2 here, I'm going to put the number 3 here, and I'm going to put the number 4 here, just to help us label the cells in that table. So when we do the two-way table and we convert it to a Venn diagram, which is what I'm going to do right now, I have my one circle, I have my other circle. Let's make it so I can see through it. There we go. All right, now I want to label what's going on. Well, the first circle I drew, that entire circle, and we need to be careful, that entire circle is your A circle. What that means by entire circle here is this entire thing, including the overlap, remember. So if I want to focus, where I focus first is the intersection, because they're very talented individuals. They can taco tongue and evil eyebrow. And so I'm going to focus on the intersection first. So I'm going to put 1 right there. That represents where both events A and B are occurring. So let's find out where is A complement. So let's find out where this one is. Where is A complement and B? Well, that would be the number 2. So A complement means not in A. So let me just kind of do this. If I want to do not in A, I kind of don't want to be anywhere inside that circle. So not in A, but I still want to be in B. So in that case, it would be this part of the circle right here. So there we have not in A, but in B is going to be that area where I have the 2. So we can kind of use the same idea for this. If I want to look at number 3, the purple 3, I want it to be in column A, but I want event A, but I really don't want event B to happen. I want the complement of B to happen. So in that case, I don't want B, but I want A. Well, that's that remaining part of the circle. So in that case, the 3 would go there. So where's the 4 go? Well, the 4 is not in A, so I don't want circle A. Not in B, I don't want circle B. Well, that means I want to be just in the rectangle, the entire sample space for it. And so we have the 4 there. And so we could see the labeling on how the cells relate to the two-way table. And again, I've said it before, I'm going to repeat it many times, is I would always start with focusing on the intersection, because the intersection is going to be the key for us. It tells us the counting in the overlap, that is the and both events happening. So the next part we're going to look at is how do we do this with just a two-way table? What does it look like with just symbols? And so in this case, let's kind of focus again. I have A complement, B complement. So we focused on the connection right here of how does the two-way table relate, the cells of the two-way table relate to the Venn diagram. Now we're going to look at how does the notation for the ands and the intersections work with the Venn diagram. So this is still your A circle, this is still your B circle, but I'm going to label it a little bit different. I'm going to label each part so we can see what's really going on. And so the first thing is this cell represents where A and B both occur. So you can see I'm going to use that upside down U. So that is the overlap. That's A and B. So that's where that one goes. So you can see how the number 1 up there and the A and B, A intersect B notation down there, they both line up still in that Venn diagram. So let's just continue down that column of A. So this is where you have event A happen and you have the complement of B happen. So I do want event A to happen. And in that case, I'm going to figure out what to do is I'm going to actually change this to the purple color for us so we can at least have a little bit of color coding matching. And so if I do that, I need to remember I want to be in circle A, but I do not want to be in circle B. And so in that case, it's this section, it's A intersect B complement. And so this column would be the complement of A. We don't want A to happen. I don't want to be in that A circle. And I want event B to happen. So in that case, remember, we have here, this entire circle is event B. So this area of that circle is A complement intersect B. You could also write it as B and A complement. Either way works. So which one am I missing? Well, I'm missing both events not happening. The complement of A and the complement of B. And that's what goes on the outside. So you can see here we just use numbers with the cells to kind of go through. But I want you to realize each cell represents an intersection of the column and the rows, whatever those labels are. In this case, it was event A and event B, or the complement of A, complement of B. So we have here our general rules. Our general rule for probability for the addition is that if you want to do the probability of A or B, I'm going to write the symbol, it is the probability of event A happening plus the probability of event B happening. But we have to be careful, minus the probability of event A and event B. And remember, in words, we can call that where they overlap. We can call that where they intersect. It is the and probability. That is the general addition rule we want to focus on. Now, if they're mutually exclusive, you can see right here, there is no overlap between them. They are completely separated. Now, in that case, their overlap is 0. Probability of A and B is 0. When they are mutually exclusive, we can just take the probability of A and add the probability of B together. So this is what we looked at in the taco tongue activity and the evil eyebrow, is how do all of these work? And the whole point of this quick notes is get us familiar with the notation. So let's go ahead and try it with a few examples. So we have this check your understanding saying that a random sample of high school students were surveyed and they were asked about their procrastination habits, and we have a two-way table of the results right here for us to look at, and we're going to choose a student at random. But first, we're defining events X as yes, someone has taken an AP class, and the event Y as yes, that student procrastinates often, how dare them. We have this two-way table of the results. And what we're going to do is let's just kind of at least label the row and column totals and the whole grand total, the table total, so we can figure out how many people were completely sampled in this or surveyed in this. So in this case, 58 and 24 is going to be 82. 12 and 22 is going to be 34, which gives me 116. So if I look at the row totals and go through 116, my column totals should match if I'm adding. So 58 and 12 is 70, 24 and 22 is 46. That does give me 116. So I do know the grand total, the table total to help me out here. Problem 1 is saying, hey, explain in plain language what does the probability of Y complement mean, and then find that probability. So remember, Y complement means the event Y not happening. And event Y is, yes, that student procrastinates often. So the probability of Y complement represents that if we are randomly selecting that student, it is the probability that student does not procrastinate often because they are a good student. And so what happens is Y complement are students that the student being not procrastinating, not event Y. So what is that probability? Well, if I'm looking at my two-way table, I want them to not procrastinate often. It looks like that's 34 total students down there. So that would be the probability of Y complement. Look at the notation. It would be 34 over 116, and that would be 0.293. So that is, do you understand what complement means? The next one says, hey, you know what? Explain why the probability of event X or event Y, either one of them happening, does not equal the probability of event X plus the probability of event Y. Then find it. So let's just kind of think through this. If I want the probability of event X, I want the probability that yes, that person is taking an AP class. So I want this. So there we are right there. Got my information. I think that's 70 total. Now let's kind of focus on the other one. I want the probability of event Y, X or Y. So I want this one too. And in that case, there was 82 total. But what's the problem here? The problem is I counted that 58 twice. They overlapped. So events yes to taking an AP class and yes to procrastinate often are not mutually exclusive. They do have an overlap in common. So if I want to find the probability, I'm going to have to subtract where they intersect because that was counted twice. And that's my work down here. Is if I want the probability of X or Y, and now you see the notation, probability of X union Y, I'm going to take the probability of X plus the probability of Y, but I have to subtract where they overlap because they are not mutually exclusive. And in that case, I do have that 70 over 116. I do have that 82 over 116 that I talked about in that table, but that 58 was counted twice, so I have to subtract it one time. 58 over 116 would be subtracted. It gives you 94 over 116, which is about 0.81. So number one was focusing on the complement, making sure we understand what it means and being able to find it. And number two is focusing on not mutually exclusive events and being aware of how we need to subtract their intersection over their overlap. So let's continue to move on with some more examples. So in this example, we're asked to take the same information from the two-way table right here and transfer it to that Venn diagram. And so what I'm going to do is I'm going to label this as my X and this as my Y, just so I understand which circle goes with which. But that doesn't mean I'm going to start with the totals from row X and the totals from row Y. Notice I removed them because I'm not going to be tempted by them here. I want to show you what's really going on. The key that I've told you before was when you are dealing with converting a two-way table to a Venn diagram, you want to focus on where they intersect. Where are both events X and both events Y taking place? And in that case, there are 58 students who take an AP class out of the 116 that do also procrastinate, slackers. And so what happens is we need to figure out where the rest goes. And so now we're going to take the rest of the table totals and column is we're looking at this, hey, yes, AP class, there's 58 who do both, but there's 12 who do not procrastinate. They're the good students. So they cannot be in circle Y at all. So this 12 is going to go out here. So notice what we've said before is that this entire circle does add up to the 70 from that entire column total. So let's see where we go next. So I do have still that 58 where they intersect, but now I'm looking at, okay, event Y is yes to procrastinating. Well, we know 58 do. Those 58 take AP classes, but we also can see that we have 24 that do out here. Those 24 need accounted as well, so they're going to be here. They procrastinate, but they're not in AP classes, so they're not actually in that circle Y. So you can kind of see if I trace it this way, you can see they're in that circle Y, but they're not in the circle X. So they're in circle Y, but they're not in the circle X. So what's left? Well, what's left are those who are not in AP classes and they do not procrastinate. So that's the 22 out here. So hopefully you can kind of see more practice with converting from a two-way table into a Venn diagram. Focus on the intersection first and then fill in the gaps. And notice it's the cells, not the totals, that go in the two-way table, from the two-way table into the Venn diagram. Now, the last one with this prompt is write the probability in symbolic form of a student who does not procrastinate often and is taking an AP class. All right, so notation time. So I want the probability of the student does not procrastinate often. So in that case, let's see, procrastinating often is Y. So I'm thinking that is Y complement. So student does not procrastinate often, so that's Y complement. Then it says right here, and. Well, that means I want to look at and. So there's my symbolic form, is taking an AP class. So taking an AP class is the blue of X. So there is my symbolic form. Now find the probability. So I want probability Y complement. So Y complement is the probability, and I'll do it in green so we kind of keep the color coding, the probability that the person does not procrastinate. So I'm right here. And I want to see where does that intersect the probability of event X taking an AP class. And so that's right here. Well, it looks like they intersect at that 12, and I believe, if I remember right, there was a total of 116. I'm not going to go to the decimal for that one, but that is the probability in fraction form. 12 out of 116. The probability that they do not procrastinate often, Y complement, and they are taking an AP class, X. So there we are with understandings of two-way tables and Venn diagrams and symbolic form. All right, so a little bit of fun here is let's do a two-way table Venn diagram of the idea that K is the event that the student in our class has gone to New Albany since kindergarten. The senior team refers to them as lifers. Then D is the event that the student in our class drives. Suppose we choose a member of our class at random, find the probability that the student has gone to New Albany since kindergarten, and so on and so on in 2 and 3. So I'm going to go ahead and fill in this table with some of the information that I've collected before, and we can discuss it. And so we could see this was a class of 28 students. I have 12 students who were lifers, were here since kindergarten, and drove to class. 4 were lifers but could not drive, and so on. So there was a total of 16 lifers in class out of the 28, which means the complement, K complement, would be 12. So you can see how I'm labeling my column and my row headers. I'm using the notation of complements. So column D is they can drive. D complement is they can't drive. So in that class of 28, 21 could drive, which means 7 of them could not drive. So we have all this information. Now let's use this to find probability. What's the probability that someone has gone to Albany since kindergarten? Now, if I'm looking at notation, what that means is I want the probability of just event K. So the probability of event K happening was all of that row. I want this entire row, which that was going to be 16 out of the 28. And so I'm just going to leave it in fraction form for right now. Now question 2 says they have gone to New Albany since kindergarten and they drive. So they have gone to New Albany since kindergarten, so right here, and I want them to be able to drive. Well, that looks like if we're focusing on the intersection there, that there were 12 students, K and D. So that would be K intersect D. Notice the notation, the symbol there. So for that one, that would be the 12 out of the 28. And so we're kind of just practicing more of, do we understand the different setups and how to go through and find probabilities from the two-way tables? All right, so randomly selected student has gone to Albany since kindergarten, or they drive. All right, so let's try this out. Probably that they have gone to New Albany or they drive, so we have the notation. So gone to New Albany, that would be a total of 16. So all right, so I do have 16. I have 16 out of 28. All right, what's next? Probability that they drive to school. So that would be the 21. So it's an or, so I'm going to add them. So I have my plus 21 out of 28. Now that would be a total for 37, and I don't have 37 students. So how did I get 37? Well, I counted that 12 twice. They overlapped. So I counted that 12 twice, so I have to subtract it. They were not mutually exclusive events. So in this case, I believe there was a total of 25 out of 28 if I do that. And then we're going to have the two-way table. And from the two-way table down to the Venn diagram here. And so if I'm looking at that, what I want to do is I want to focus first, like I said, where they intersect. And where they intersect is they are going to intersect at event K and event D, which was 12. And so this circle out here represents, we'll just say, all of K. And so if I'm doing that, what I want to realize is that I need to make sure that I have K, but I do not want D. So I want event K, but I do not want D. And so that would be this part right here. I want K, and I do not want D. So that would be 4. Which makes sense because there's a total of 16 in that circle. And that is what I could see, what I wanted up here. So this event out here is its event D, but I do not want K. So I want event D, but I do not want K, so I think that's 9. And again, that should make sense because that circle right there should add up to the 21, and it does. So I see the 4, I see the 12, I see the 9. What I don't see is I don't see the 3 because that is out here. So what does that represent? That represents the students who are not lifers and they cannot drive. So that is a two-way table for us to kind of go through the process and the conversion. All right, so one last example for this video. So right here, we are going to look at the different notations one last time. According to the CDC, Center for Disease Control, back in 2015, 57% of people had landline phones. What's that? 89% have a cell phone, 48% had both. Interesting. So I'm just going to fill this in to kind of save some time and just discuss what's really going on. Since we've done examples like this many times, we're going to look at this a little bit faster. So in this case, I'm going to define L as people with a landline phone and C as people without. So notice how I'm labeling my table down here. I have a row for L and I have a column for C. So the other row and the other column have to be their complements, L complement and C complement respectively. And so if I look at what was given to me, I was told that 57% have a landline. So notice where that went. That is the total amount of people who have a landline. I was told that 89% had a cell phone. That's a total for those that have a cell phone. And then I was told, you know what? 48% have both. So that would be the intersection. So the question you have to ask yourself is, how did I get the rest of the information? Well, you do realize all of them have to add up to 1 on the total. And so once I figure out that I'm going to focus on really, I'd say on, let's look at the column right here, is if I know 48% have both, but only 89% have just a cell phone, I can figure out that this is 41 because it has to add up to 89. And it's the same. Right here, I know 57% have a landline. Of that 57%, 48 have the both with the cell phone, so if I can find that 0.09 by subtracting. And then I now know this, I now know this, I now know this, I can figure out how to get that 0.02. And that allows me to fill in all the information in this table. And you can see how I transferred it over to the Venn diagram. We've already focused on how the cells relate. Remember, 0.02 are those who are not in it. 0.48 is where you should focus. It's where they intersect first. And then we can see, hey, this needs to be in L, but it cannot be at all in that C circle. This needs to be in C, but it cannot at all be in that L circle. So this was a quick just visual for us to kind of look at. So we've done this many times already as we go through. Now there is one last Venn diagram that you do need to look at. And I think it's really important, especially with this video. So what's going on is right here we have one of the circles of the Venn diagram, and this is, well, pretending to take notes while the video lesson is playing in the background. And then right here are, secretly looking at Venn diagrams. This is where you are right now during this video. You are pretending to take notes while the video lesson is playing, and you're secretly looking at Venn diagrams. So a little bit of humor of Venn diagrams at the end of this video. Hope this helped with the addition rules for probability.